So we'll now move over to variables and memory access. So let's look at program and data memory. We'll start with a very simple program. So we have this program int main, and it defines three variables, x and y. It initializes them, and it says that z equals x plus y and returns z. What's going to happen here is that the compiler is going to translate this high-level language, this C code, into machine language or binary. So how is it going to do that? It's going to take the code and put it in the text area, and it's going to take the data and store it in the data area. So both the instructions and the data are mapped to the address space of the system according to the memory map. So we had this memory map here that we saw last lecture, and in a von Neumann architecture, we know that instructions and data are basically the same thing. They're both just data, and they're just stored in different places in the memory map and the address space of the processor. So that's what happened here. The code went into the text area, and the data or the variables were stored in the data area. Okay, so how does that go? Actually, the text area is going to be mapped into the instruction memory, and we're going to use the program counter to point to the instructions inside the instruction memory. Now, this is a Harvard architecture, so we have this separation between instruction and data memory, but in general, they share the same memory space because it is a von Neumann type of architecture. Okay, the global variables and static variables and others, they're going to be mapped to the data memory. So actually, this is not accurate here because main is going to have local variables, but I just wrote it as such that x, y, and z would, if they are globals, they're going to be already stored here inside the static data area, and the global pointer is going to show us where this static area starts. We are going to use load and store operations that are going to move the data in and out of the registers that are inside the register file in order to do operations on them. So let's look at variables in C. So variables are declared, defined, and initialized in C. They have a type qualifier such as const, volatile, and static. They have a type modifier such as short, long, signed, and unsigned. They have a data type such as int, float, char, and void. They have the variable name, and they may have an initial value. So examples of this are const, unsigned, char, foo, which equals 12, or long, int, bar. Those are two types of examples that use some of these, and some of them they don't use. What you have to have is a variable name and a data type, of course. So what happens when we do such a declaration, definition, and initialization? What is going to happen is that the compiler is going to allocate space inside the data memory according to the data type. So global and static variables are going to be allocated in static data, and we'll see later on that static variables have this scope that is for a particular function. And we can see that the different types in C, they have different sizes in the architecture. So in RV32, which we're using as an example, a 32-byte bit version of RISC-V, chars are going to be 1. That's actually going to be true for pretty much every programming language. Shorts are going to be 2. Ints are going to be 4 bytes, so that's 32 bits. But longs are also going to be 4 bytes, whereas in RV64, a long is going to be 8 bytes, and so forth and so on. We get the different sizes of the data. So that size is going to be allocated inside the memory for the compiler to use. Okay, local variables, which are also known as automatic variables, are going to be allocated on the stack. Each function is going to have its own stack, and so we're going to allocate room for these variables on the stack of the function because they're local to that function. And again, we're going to discuss that a bit later when we discuss scope. The compiler can also allocate local variables to registers. So it only really needs to use the stack or the static data if it doesn't have room inside registers or it needs to store some of the data. So if it can, it just can allocate them to registers and thereby save memory accesses. One of the keywords that we probably haven't seen before or at least not much from a previous C course, is volatile. So a volatile keyword is something that's not used in general programming very often, but it's used a lot in embedded systems. So we have different types of variables that aren't actually used in a programming way because they point to something that would be an output or something like that of our block. And since it's not used, the compiler would see it and just clean it away, say this is unuseful and not needed, and it will just erase it. If we use the volatile keyword, that means do not remove it to the compiler. So we'll see this volatile keyword showing up very often in embedded C code. The other thing is that we have the constants. So constants are something that are not going to change, and therefore they're stored in a read-only section of the memory because we are not allowed to write them. And if we try to access a read-only section, then it should, the operating system or something else should recognize that that is something that is illegal. So if that was in C, how do we access the variables at the assembly level? So RISC-V is a load store architecture, which means there are no memory-to-memory operations. In other words, if there are no memory-to-memory operations, all we need to do is load commands, which will bring data from the memory into a register, and then store commands, which are going to write data back into a memory. And this is done in RISC-V with only one addressing mode. So we saw in the last lecture that there are several addressing modes, and there are actually many more, but RISC-V really simplified this by only using one, which is displacement addressing. And this is supported by the I or S formats, where the difference between the I and S formats is just if these 5 bits are a destination or a source operand, which we'll see in a second. Okay, so this is what we saw as displacement addressing. And what exactly it means is that RS1 is going to point to a register, as we see that the register holds the 32-bit address that can access the entire memory. Okay, so we point to a register, and then with one level of indirection, we go and we get the actual 32-bit address using only 5 bits that are inside the instruction itself. The immediate here, it shows an offset from that register. So this can be a starting point, and then we can jump from there quite a long ways because we have 12 bits over here, which is 4,096 bytes, which we can jump from that place forward, backwards, and so forth. So we can reach a lot of memory around a certain starting point that we store inside a register. And then RS2 or RD is going to point to another register, which also we can either take data or use as a destination, as we'll see in a second. Okay, so for example, we have word access commands, LW and SW. There are also byte access and so forth commands. So when we use a load word command, what we're going to do is we're going to say load word x6 123 x10. That means we should store inside x6. We should load into register x6 the memory data that is in the address that is stored inside x10 plus an offset of 123. So this is saying 123 offset from address x10. So in this case, we're going to have x6 is going to be the RD, the destination register over here. We're going to go to the address inside x10 over here. We're going to see what that is. And then from there, we're going to go 123 bytes forward. We're going to take that data, and then we're going to store it inside a register that is addressed by RD, which is going to be x6 in this case. For the store word, we have store word x6 equals 123 x10. That means that we're going to put x6, whatever is stored inside x6, we're going to store it in the memory address that is at x10 plus 123. So in this case, we're going to use RS2. That's the S format. So x6 is going to be the actual data that we want to store. It's not going to be a destination. It's going to be the data that we want to store there. And RS2, or the opposite, I can't remember which, is going to be the displacement addressing. So how do we access an absolute address? An absolute address is a kind of a problematic thing because we need to load a 32-bit value into a register. But if we look at our I format, which had its constant inside, it only has a 12-bit value. And we want to load an absolute 32-bit value into a register, but we only have 12 bits available in the I format. So I guess the I format may not be the right thing. Well, We actually have the U format, which we briefly looked at, which has a 20-bit immediate. So it only has a destination register. We want to store something inside, some constant inside a register, so we don't need another source operand. We can just have the destination register that we want to store it in and use everything over here as an immediate. And therefore, we get 20 bits. But 20 bits is still not 32 bits. If we have pretty big values, we can store them immediately inside our D here with this one command. But what happens if we need more than 20 bits, 21 bits or 32 bits, etc.? So how do we do that? Well, we need two commands. The first one is called load upper immediate, or LUI. And what that is going to do, it's going to take whatever constant we had here, and it's going to shift it left by 12 positions. So LUI T0 456 is going to be T0 equals 456 shifted left by 12 positions. So it's going to go, and in the destination register, in the top 20 bits, it's going to store whatever was the constant over here. And then we can use add-I, which has 12 bits in its immediate, and just store the bottom, the lower 12 bits. So add-I T0 789. So what we're going to get is T0, which was equal to 456 divided, shifted left by 12, is now going to be added to it 789. And therefore, we can fill in the whole 32 bits, the 20 MSBs with this command, and the 12 LSBs with an additional add immediate command. Another option is to create a PC relative address. So we can use a different command, which is add upper immediate to PC, or AUI PC, which is going to do the same thing. It's going to take the program counter now as a reference, but we don't need to actually tell in our instruction what the program counter is, because that is one like hard-coded register that it's going to use. So it's going to use the program counter, and it's going to add displacement to it and shift it to the left, add displacement, shift it to the left, and then we can use add-I to add the LSBs to that. So that's going to be useful to have a PC relative type of addressing if we need to use it. So what happens on the C side? When we declare int my data equals hexagon 3, what the compiler is going to do, it's going to, well, int we saw is 4 bytes. So it's going to allocate 4 bytes of memory to hold the variable. So what we did here is we allocated 4 bytes, which is going to be address 1000. This is byte number 1000, 1001, 1002, 1003. So it's going to allocate those 4 bytes. Then it's going to place the value 3, which is 0003 in hexa, into those 32 bits. And remember, we're here with the little endian, so it's going to be 0003. It's going to store into those 4 bytes. Okay, and it's going to associate an address. So since it's stored it over here, and the address of where it starts is OX1000, that's going to be the address of this my data variable. When we write my data, we're actually referring to the data at address OX1000. So when we write in our code my data, we go to address OX1000 and look at the data here, and we see that it's 000003. Okay. We actually have a special variable that's called a pointer that we can store the address in. So if we write something like this, int star my data equals and my data, what that is going to do, it's going to create a variable of type pointer to int. So my data pointer over here is going to be a variable of type pointer to int, because we wrote int here and we called it a pointer in its declaration. And what it's going to do, it's going to have the address of my data, and we saw that the address of my data is 1000, so it's going to store 1000 inside this pointer. Okay, so in a 32-bit ISA such as RV32I, the pointer will always be 4 bytes. So all types of pointers are going to be 4 bytes. So somewhere over here, we're going to create this variable, my data pointer. We're going to allocate 4 bytes for it and store inside the address of what it's pointing at. So my data pointer is these 4 bytes, which are essentially, they store 0000100000, and it's going to be pointing at this address over here, which is what the variable my data is. As I said before, this and is an operator that returns the address of a variable. So when we write and my data, it's going to return 1000 over here. And an easy way or just a tip how to read the declaration over here. So I'm talking about a declaration over here. We have this part. We're going to start from right to left. We read my data pointer is a pointer. That's what this star says, to ints. So it's pointing to an area that is going to be 4 bytes long, 32 bits long. So a real cool thing that we can use is called pointer arithmetic. For that, we need to use what's called the dereference operator. So what the dereference operator does, it returns the value that is pointed to by a pointer. And this is where things get a little bit confusing until you get used to it. So here we have a declaration int what is pointed to. So we created a variable called what is pointed to. And we say that it's equal to the dereferencing of my data pointer. So as we look here, my data pointer is 0x10000, right? Which is basically the address over here. So when we say dereferencing, what we say is, look at what that's pointing to. It's pointing to this value, 0x0003, right? And take that and now put it into what is pointed to. So what is pointed to is now going to be a new variable, and the variable is going to get this value over here. So what is pointed to now equals 0x0003, okay? Now, what happens when we assign a value to a pointer? It will store the value at the address that it is pointed to. So we have this declaration over here, some other value that's equal to 0xFFFFF. That's going to create us a variable called some other value. It's going to get, the value, whatever we initialized it with. And now what we're going to say is a dereferencing of my data pointer. So look at what my data pointer is looking at. That's this 0x00003, okay? This place over here. Instead of having that, it's now going to get whatever we have inside some other value. So we take this value at some other value and put it where my data pointer is pointing. Okay, so we overwrote whatever was in my data, in this case, whatever was pointed to by my data pointer with the value that was stored inside some other value. So that's what dereferencing does. And what that allows us to do is to add scalars to scalars to the pointers. And what it is really cool about that, the pointer has a data type. So it's a pointer to int or a pointer to char or a pointer to something else. And when we add a scalar to it, it's actually adding a number of sizes of that type of a variable. Okay, so we're going back over here and we have my data pointer that's pointing to the variable my data, as we saw here. If we do something like my data pointer plus plus, so we're going to increment my data pointer, we're going to say my data pointer equals my data pointer plus 1. That's equivalent to saying my data pointer equals my data pointer plus whatever the size of a pointer to my data of the pointer called my data pointer is, or whatever it's pointing to, excuse me. Okay, so my data pointer was a pointer to int. An int is size 4. That means that what this is going to return 4. So it's going to be my data pointer plus equals 4. Okay, let's see how that happens, right? My data pointer went from 1000, it was added 4 to it, 1004, which means that essentially instead of pointing at my data now at address 1000, it's pointing to the next word, which is at address 1004. And again, if we increment it again, it's going to go point to 1008, etc. Okay, this is really useful for iterating over arrays. So we can go to the start of the array, which is at a first address, and then go just plus plus. It goes to the next value in the array. And since we declared whatever the pointer was to a pointer to a certain type that the array is the same type, it's going to exactly jump by the increment of the single element of the array. So RISC-V's displacement addressing makes this easy because, as we saw before, the source register does this indirection where we have the address of basically where something starts, and then we have the immediate, which is how much we want to actually increment from there. So that's why displacement addressing is really useful, and it's enough to supply all our needs in RISC-V. So I just mentioned arrays a bit. Let's go back, let's go and emphasize or detail what exactly arrays are. So an array is a set of items that have the same type and the same variable name. And in C, it's very important to understand that arrays are stored in contiguous memory locations. So if I do something like this and write int A4, what's going to happen is we're going to allocate a static array of 4 ints, which are going to be contiguous in memory. So it decided to allocate A0 at the address 1000. That means A1 is going to be at address 1004, A2 at 1008, and A3 at 1000C. Okay, so they're going to be in contiguous memory locations, and that's a real important thing. If we do something like char C50, we're going to have a static array of 50 chars. So each one of them is going to be 1 byte, but they're going to be set one after the other one in memory, going like this, right? That's how my picture is built here. Okay, therefore, the address of the first element of an array is just a pointer to that array. So when we say something like that, you know, a pointer to A is a pointer to an int, and it's equal to the address of A0, okay? So it's going to be equal to 1000 over here. That's just like saying that pointer to A, which is a pointer to int, is equal to A. So the address of A0 is the same as A, which is the name of the array. So the name of the array is basically the address or the pointer to the first starting point of that array. And that's really, really useful. Okay, and so we got pointer to A, which is basically is now pointing to that address. It's storing 1000 and it's pointing to A0. Okay, now incrementing it, we can move the pointer through the array. So pointer to A++ is going to be the same as saying, you know, pointer to A equals and of pointer to 1. Okay, so what that's going to do is going to change here to 1004, and we're going to now be pointing at A1 instead. We can say something like this: the pointer to A3 is a pointer to int that's equal to the address of A3. That's the same as saying that pointer to A3 is equal to A plus 3, and then it's going to get 10C, and it's going to point to A3 over there. So all of those are the same types of things, and that's called pointer arithmetic, where we can go and add scalars to a pointer to move forward and back, basically inside an array. So that leads us to a string, which a string is just an array of chars. So chars are basically is a data type that was made to hold ASCII, which is 1 byte, and there are 256 values in ASCII and basic ASCII, which is a character, and that's what it was built for. Okay, so a string is just an array of chars in C that ends with the null character, which is the character /0, and so you can just declare it as a pointer with a literal. So if I say char pointer to string equals str in quotes, what that is going to do is going to make a string that is 4 characters long that is going to be built str and /0. And if we look inside the memory, as we said, this is the lowest address. This is byte 0, byte 1, byte 2, byte 3. It's going to put str and /0 in contiguous places over here. And when we just say str, what we're talking about is basically the first address over here, the first element of the array, or str0. Okay, so all of those are the same thing, and that's really useful to use and to iterate over arrays and strings and so forth. So just as a summary of load and store execution, C variables are stored in memory, and they're loaded into registers for execution. Displacement addressing is used by placing a memory address, which is basically a pointer, inside a register, and using an offset for indexing the array or the string or whatever. Okay, so if we have some simple C code, A12, that's an array, the 12th or actually 13th position inside the array is going to be equal to H, which is right now some value that's stored in T2, plus A8. So we know that the base address of A is stored in T1. What is going to happen when we compile that? We're going to go and we're going to load word into T0. What word? We're going to take the addresses stored in T1. That's where the pointer to A is. Okay, and we're going to add 32 bytes because the offset of 8 means 32 means 4 times 8. So it's going to go from wherever T1 is pointing to and add an offset of 32 to it. Then it's going to add T2, we said has H inside it, so it's going to add T0 and T2 together and store that in T0. And then it's going to store it back into A12. So that's going to be, again, the base address of A, which is stored in T1, with an offset of 12 units, which is 12 times 4. So that's going to be 48. Okay, so how do we do this? We have to have a 2 read and 1 write register file. So our instruction is going to come, and we're going to break it up in looking at the different bits. So the 2 source operands are going to go in order to read out the read data. The destination operand is going to go and address our write register. And what we're going to do is we're going to take the first source operand and bring it to the ALU. The second source operand will potentially go through the ALU, but it could be an immediate instruction. And in that case, we're going to take the immediate from the instruction, add sign extension to provide a 32-bit instruction in a 32-bit constant, and direct that into the ALU. Then we do the ALU operation on this type of a thing, and that actually can be the basis for addressing our data memory, because because we're using displacement addressing. So we may have had to take some base address and add to it with the ALU some sort of an offset. And that will provide our address to the data memory. We also may provide the write data directly from the second operand. Okay, and that we're going to store, or if we read back something, then we can either take the output from the ALU and directly write it back to the register file, or take the output from the memory and write that back to the register file. So this is kind of the way that we could implement a RISC-V architecture, or the basic part of the RISC-V architecture.